Boston got it done. Be a good game 4. Okay, still into modular arithmetic, I guess is what you call this, and trying to show that this huge number, 3 billion and some change here, is divisible by 11. Okay, now it turns out there's a nice result with congruences. It makes this fairly tractable, fairly manageable. Now, the very first thing I did write down here is just write 3 billion, I won't say it, in its expanded form, 3 times 10 to the 9th, 1 times 10 to the 8th, all the way out. Now, notice I left, there happened to be a 0 at the end of this, so I just left that out since it doesn't plan. You know, technically we should have plus 0, I guess, out here, but it really, obviously it doesn't make, we can omit that. Now, what we're going to do is turn this into what they call a congruence. It's referenced as modular arithmetic in number theory books quite a bit, but showing that this large number, L stands for large, that's not a bad choice of letters. L is divisible by 11 is equivalent to showing that L is congruent to 0. Now, what this means is L minus 0 is divisible by 11. So an example would be 88 minus 0 is divisible by 11. 8 times 11 is 88. So it turns out you can treat this triple horizontal equality much like just the basic equality that you're familiar with all throughout your math career. Now, what makes this thing work that, you know, you might be wondering about divisible by 11 is this truth right here. 10 is congruent to minus 11 because 10 minus a minus 11 is 11. Of course, 11 is a divisor of itself. Now, this truth not quite as obvious. You can raise this equality, and just if you think of it as an equality, if this was a regular equality, you could raise both sides to any power you wanted. The very same thing is true. You can prove it using the difference of 2 squares for the case n equals 2, the difference of 2 cubes for n equals 3. And there's a similar algebraic identity, factoring identity that you can use for any n. But for now, just this example should suffice. 10 squared is congruent to minus 1 squared. Again, I squared both sides of this equation, let's call it that, because 10 squared is 100, minus 1 squared is 1, 10 minus 100 minus 1 is 99, and you get divisibility by 11. Now, here's where the power really takes over. You can use this as a substitution all over the place. Notice how we have 10 to the n here, 10 to the 9th, 10 to the 8th, 10 to the 7th, 10 to the 6th, 10 to the 5th, all the way down. That's exactly what we do. We take our L and replace with minus 1. Okay, like right here, 10 got replaced with minus 1 because 10 is congruent to minus 1. And also 10 to the n is congruent to minus 1 to the n. So literally you can treat this just like an equality. It's really cool. There's some certain things you got to be careful about division when you're doing modular arithmetic, but in general, you can treat congruences just like equalities. And so you can multiply stuff together, add congruences together, so on and so forth. So it's really nice. And you can see all the way across, I just replaced with the power 10 with minus 1. Notice right up here, we have 8 times 10 to the 7th. Okay, well, 10 to the 7th got replaced with minus 1 to the 7th. All the way out, folks. And now all the way out to where we get to minus 9 here. Now, the cool thing about all this is that minus 1 raised to an odd power is just a negative, right? Negative 1 raised to any odd power is still going to be negative. And so that's where we get minus 3 right here. Okay, minus 1 to the 8th. I won't go through the whole thing, but this is why we have the alternating process here. It alternates precisely because these odd and even exponents alternate in this positional expansion. Okay, and so these numbers on the next line, all these numbers sum up to negative 22, which is congruent to 0 because 11 divides 22. 22 is a multiple of 11. So we finished the problem. We did what we set out to do. This is equal to 0. Just like right up here at the very beginning, we said that we could show divisibility by 11 by looking at this congruence. That's exactly what we've done, folks. We got the sum of the digits in an alternating fashion to be equal to negative 22, and that is congruent to 0 mod 11, and we proved what we set out to prove. Hope you enjoyed.